Right. So we'll continue now, and what we have set ourselves up to do in this segment is to define this idea of a derivative of a functional with respect to the function that is its argument. Okay? So we are going to define this idea of the derivative of the functional pi with respect to the function u. Okay? Okay. Let me go to a diagrammatic representation of what we are trying to do. I'll first tell you what we are not trying to do. Okay? And what we are not trying to do is define the derivative of a function. Because if we were indeed working just with functions, this is what we may be aiming to do. If we had a function f of argument x, okay, f is a function of x, and maybe the function looks like that. Okay? We are not attempting to do something like saying, okay, around this point x, okay, around this particular value of x, it's not like we're just trying to define the derivative of f around x, because we know very well how to do that, right? We're not going to describe the procedure here, but we know that if we end up doing this, then we get this the idea that the slope of that line that I just drew is the derivative df dx. Okay? And you remember the process, and the process by which we would do this. We would consider, from first principles if you like, small variations of x around that value. Okay? So we may say, okay, we have x, we take some variations, let's call them dx maybe. Okay? And we know that if we take those little variations around x, we know that, well, if we take those variations, the function f itself also varies by some small amount delta f. Okay? And really this df dx is the limit as delta x tends to 0 of the fraction delta f divided by delta x, right? This is our notion of the derivative of a function. Okay? So this is the derivative of the function f of x. This is not what we're trying to do. The situation we have is really quite different. It is the following. I'm going to draw this out in 1D. Okay, so in particular, let's assume that our displacement field u is applied to a 1D problem. So here we have the position, right? Or because we're writing it as a function of reference position, let me use capital X here. Okay? And we have a 1D problem, so we have our displacement field u. Let's suppose that our displacement field is such that it does something like that. Okay? And this is L. Okay, so really the picture could be something like, we have a problem in 1D, right? This is 0, that is L, and we're talking of how, and that is some general position X. We want to know what happens now, maybe as we apply a traction T to this body, right? We want to know how the displacement varies, right? We want to know how much it stretches. And maybe this plot that I've shown you here on the right-hand side is a representation of the displacement. Okay? And now remember that associated with u, okay, we know that we can now also get our energy function or pi of u. Okay? What we are trying to do is understand how pi varies when the entire displacement field varies. Okay? What we want to do is vary the entire displacement field over the entire domain. So maybe we want to do something like that. Okay? All right? And everywhere I could define this difference between the original displacement and the sort of perturbed displacement, right? Or the varied displacement, right? I've applied a variation to the displacement here. Okay? I am going to say that this field that I have now is u plus some variation, okay? And I'm going to write that variation as epsilon times w, okay? Where I'm going to just rewrite that including arguments, okay? I'm going to rewrite that as u function of x plus epsilon, and epsilon is not a function. Epsilon is just a scalar, the way I want to write it. Epsilon times w of x, okay? So really what we've done here is to say that, well, you know, that original displacement that we had u, and u is this. The red field here is u. Okay, the green field is ux plus epsilon w. Okay? In this setting, okay, we are thinking of w of x is the variation on u of x. Okay? Epsilon is a scalar. Okay? And the idea of the scalar is the following. We have decided that we want to carry out a variation of u using this new field that I've introduced, w. Epsilon sort of lets us control how much I want to vary u. Okay? Right? So just a scalar, right? Just a multiplier, right? Do you want to have a lot of variation with w or just a small amount of it? Okay, and the whole point is we want to be able to control the amount of variation separately of the variation function itself. Okay? Right? So w, you know, is a variation, and you note, of course, it's a function. Okay? Just like u is a function, w also is a function. Okay? So epsilon, however, is a scalar that controls the, let me just say, the amount of the variation applied to u of x. Okay? That is what we're doing. Okay? And straight away you note that I'm calling this a variation. It is indeed a variation on our original field u. It is from this object that the term variational methods or variational principles arises. Okay? Because all the arguments we're going to construct are based around this idea of taking variations. Okay. So we've decided this. We said, and now we've decided that we have our original field u, we are going to apply a variation onto it, and we're going to control the amount of variation, okay? What you should be noticing now is that we are actually taking this original idea of how we took derivatives of functions from first principles by doing a variation on x, right? We're really taking this idea and beginning to generalize it to this notion where we have a functional, okay, whose argument is the entire function, right? Because now we're already talking of how to vary the function and what it means to vary the function. Okay? So keep that in mind. Now, it turns out that we cannot apply completely arbitrary variations W. The variations W have to respect certain rules. Okay? And here are the rules. In order to understand the rules, let's go back to U. Recall that U belongs to that functional space S, remember? We can make that functional space a little more specific, right? We can say that S consists of all U, right? And maybe these U's are polynomials, exponential functions, or whatever, right? Don't worry about that, okay? S consists about, don't worry about that right now. So S consists of all U such that vertical bar means such that, okay? Such that U of X, comma T equals U bar of X, comma T, okay, on the displacement boundary. Okay, U bar is just our displacement boundary function. Right, it's just the value that our displacement field has to take on the relevant part of the boundary. Okay, and this is something that we've alluded to in the past. We've talked about the fact that if this is the body in the reference configuration, we have our traction boundary, of which we've said many things, right? We've talked about how the complement of the traction boundary is the displacement boundary, right? How on this boundary we have U equals U bar, right? Okay, so that's what we're doing here. Okay, so we're saying that, to make S a little more special, or not just not a little more special, but to be more specific about what S is, we need to also include the fact that, we want to have this displacement field that we want to know more about. We need to have it respect the boundary condition we're applying on the body, the displacement boundary condition. Okay? So essentially what we're saying is that U satisfies the displacement boundary condition. Okay? That's what U is about. If you remember a couple of minutes ago, I said that what we want to know is what W can be like. Okay? Now, for W, because we're going to take some variations on U to understand more about about how pi varies, right? That's what we've introduced W for. Well, W had better not change the displacement boundary condition. Okay? If we have our body in the reference configuration, right, and now let's suppose that over the blue part of the body of the boundary, I'm specifying the displacement, right? So that's the displacement boundary. In order to do this mathematical argument of what the variation of pi is, right, to define this derivative of pi, I've introduced these variations, right, this variation field, W. I'm saying that I'm not allowed to introduce a variation that changes the displacement boundary condition, that violates the displacement boundary condition. Because if I do, I fundamentally change the problem. Okay, and I'm not allowed to change the problem in talking about derivatives. Otherwise, I'm talking of solving some other problem. Okay, so that's the importance of saying that W has to satisfy this condition, right? And in particular, it shouldn't violate this condition. Okay, all right. Or alternately, U plus epsilon W also must satisfy U plus epsilon W equals U bar on that boundary, on the displacement boundary, okay, for all W, well actually not for all W, it needs to satisfy it for all values of the scalar epsilon, okay, epsilon is a scalar, right? For any value of epsilon, it has to satisfy it. But what does this mean? What this means is that W must be equal to 0, dead 0, on the displacement boundary. Okay? And by so doing, we have introduced the idea that W itself belongs to a certain function space, right? So we can say this. Just like we said U belongs to S, we can say W belongs to some other function space, V. And what is V? Well, maybe V is polynomials just like U is, or maybe, or it could be exponentials if U is exponentials and so on. However, V consists of all functions W such that, okay, W of X equals 0, okay, it vanishes on the displacement boundary. Okay, so reference configuration, if the blue part of the surface is where I have displacement boundary conditions specified, in the process of defining these derivatives, I'm not allowed to consider functions which will change, which will give me, which will change that displacement boundary itself, displacement boundary condition itself. Obvious, right? Seems like a reasonable requirement. Okay, and that means that we need to have W belonging to the space V, okay, for our variations W. Okay, well, let's see what that lets us do now. Okay, so what we want to do is the following. We are still trying to define what it means to take derivatives of pi. I am going to consider the following function. I'm going to consider a function, the following form of the functional. I will denote it as pi sub epsilon, okay, which is defined as pi evaluated not with U, but with U plus epsilon W. Okay, and in fact, for brevity, I will also use the notation U sub epsilon for that. Okay, for the the variation added to U. Okay, right. So equivalently, I may say that this is just pi evaluated not with U, but with U sub epsilon. Okay, we're now coming to the so-called business end of this segment. We still want to define that derivative. Here's how we could do it. We could say that, all right, now if I'm applying these variations to U, I can evaluate pi with those variations, right? So I could consider pi evaluated at epsilon, right? Okay. Now, in order to know how pi changes with the amount of this variation, what I can consider is taking derivatives of pi with respect to epsilon, which is a scalar, right? Which is a well-defined thing. It's not a vector, it's not a tensor, it's not, it's just a scalar. And we know how to take derivatives of everything with respect to scalars, okay? So we can take this derivative, because now what it means is that if I have this field here, if I have u, x, right, and if this was my u, okay, and if now I am talking of doing variations on u and I get this varied field, right? Okay, observe that even my varied field is still satisfying the boundary condition, right? Okay, so in fact what I could say is that in this one-dimensional setting, okay, this point here, x equals 0, right, is that. Okay, and there I'm making sure that both u and my varied function u plus epsilon w, okay, that is u. Sorry, we're all in 1D, so it's a scalar, right? That is u, and the green function is u plus epsilon w, which is u sub epsilon, right? Okay, observe that that also satisfies my displacement boundary condition, right? So w indeed is equal to 0 at x equals 0, which is my displacement boundary. Okay, what we're saying is that now for this varied displacement function, let's look at how pi varies with respect to epsilon. And remember, epsilon controls the amount of variation I'm putting. So you're saying, okay, put a little bit of variation, look at how pi changes, and look at how pi changes with respect to the amount of variation you're adding. Okay, so effectively, we are trying to find out, we're trying to check how much pi varies with variations in u, right? But now, because of the form that we have here, right, for every value of epsilon, we're controlling how much variation we put on u. Therefore, effectively, when we compute this derivative that I've just written here, okay, this quantity is the variation in pi, okay, with respect to variations w on u. W is a variation on u, right? We're controlling how much of that variation we are putting by controlling by specifying epsilon or by introducing epsilon. Okay, then by looking at this derivative, we are effectively checking how is pi varying with u. Okay, but here's the deal. Remember how in computing the derivative, we finally said, yes, the variations have to shrink to 0, right? In computing the standard derivative, right? Recall that df dx, where f is a function of x, we say that it is the limit as the variations in x go to 0, right, of this ratio. What that suggests that in doing what we're trying to do here, we need to have some way to say that, all right, we want to look at how pi is varying with respect to u, which we've done, but we want to know how it's varying with u as those variations shrink to 0. And now again you see the role of epsilon, because we could just take this derivative that I've circled, compute it, and then set epsilon equals 0. That gives us the notion of our derivative. Okay? So what we want to do here is equivalently consider derivative with respect to epsilon of pi evaluated at u sub epsilon, right? And in general, we are looking at vectors, though my example here is 1D, just to help me draw it. Okay, so we've introduced the idea of taking this derivative with respect to epsilon, but then we just want to set epsilon equals 0. Okay, so now we are doing what I've been outlining here in this plot. Okay, we're taking derivatives, we're looking at how pi varies as we are varying the displacement field, but then we're saying that we want those variations in the displacement field to go to 0. That is what we're doing by specifying that we take this derivative with respect to epsilon and set epsilon equals 0. This is our notion of the variational derivative of pi with respect to u. Okay? It is variously written as either delta pi respect to delta u. Okay? This is just a notation, right? Or that. Okay? Okay? This is the variational derivative of pi with respect to u. Okay? All right. So we've done what we intended to do in this segment, which is motivate and define this idea of taking a variational derivative of a functional, right? Remember, pi is a functional, it's not just a function. Okay? We've defined what it means to take a derivative of a functional with respect to the function that is its argument. When we come back, right, in the next segment, we are going to apply this idea to our Gibbs free energy functional and see where that takes us. Okay, we're going to do that in order to define this notion of equilibrium. Okay, all right, we stop.